All right, EEE 203 practice final problem number 2. Consider the following interconnection of CT-LTI systems. We have a signal X of t going into H1 of t, which is in series with an H2 of t. This whole thing's going to make up H of t. Right off the bat, we know in the time domain that this would be equal to H1 of t convolved with H2 of t. And we want to figure out what the Fourier transform of H1 is, of H2, what the overall frequency response H of j omega is, and what the overall impulse response is. So for part A, we want to know big H sub 1 of j omega, and that's equal to the Fourier transform of t times e to the negative 2 t u of t. And unless the question specifically says use the integral, you don't have to use the integral, you just use a table. And right from the table, we know that this is going to be equal to 1 over 2 plus j omega squared. So there's part A. Pretty simple. Part B, we want to know big H sub 2 of j omega, and that's the Fourier transform of sine of 0.3 pi t. So this right here, sine 0.3 pi is omega naught. And you can just, again, use the table. And what you're going to get is you're going to get pi over j times delta of omega minus 0.3 pi, right? Yep. And then it's a sign, so it's a minus sign, delta omega plus 0.3 pi. So there is part B. Now, what is the overall frequency response H of j omega? Well, we know that H of t is equal to H1 of t convolved with H2 of t, and in the frequency domain, when we have two systems like this and connected in series, convolution becomes multiplication. So big H of j omega is equal to big H sub 1 of j omega times big H sub 2 of j omega. And we can work that out right now. We'll get that H of j omega is equal to, we have 1 over 2 plus j omega squared, and that's multiplied by a pi over j times delta of omega minus 0.3 pi minus a delta of omega plus 0.3 pi. Now, this is H of j omega, but let's keep going here. We'll just leave this pi j up front. So we'll do pi over j, and we'll distribute a delta. We'll distribute this right here to each delta. So then we'll get 2 plus j omega squared in the denominator, and we'll have a delta of omega minus 0.3 pi, and that's minus a delta of omega plus 0.3 pi, and that's all over 2 plus j omega squared. And there's one more step we can take here, and that would be, let me just double check the property name. It's the sampling property of the delta function, right? The sampling property states that x sub t times delta of t minus t naught is equal to x sub t, or x of t naught times delta of t minus t naught. Now, in the frequency domain, J omega in the Fourier domain, J omega is our t. That's our independent variable. That's the variable that's on the horizontal axis. So we're just going to apply the sampling property to this. And here's our t naught right there and right here. So one of them's a plus and one of them's a minus. So that means that h of j omega is going to be equal to pi over j, and we'll have delta of omega minus 0.3 pi, and that's going to be over 2 plus j times 0.3 pi, and then minus delta of omega. And I'm going to rewrite this just so everybody can see it, 0.3 pi. Because now this minus sign's here. This isn't the plus sign here. That's a minus sign. So now we can see that we're at a negative 0.3 pi, and we'll get 2 minus j 0.3 pi. And that's that. That just gave us C. Let me get some room here. So there's C, and now C's all ready for us to get back into the time domain. Now we got a whole bunch of J's here and everything like that too, but these J's, they're complex numbers, or we have complex numbers, but they're still numbers. So we just treat them like numbers. Now for part D, we want to know what the overall impulse response. Now we just got to go from the Fourier domain back into the time domain, and again, just use your tables. And actually, let's expand this a little bit. So we'll have pi times delta omega minus 0.3 pi, and I'm gonna write this right here. It's gonna be 1 over j times 2 plus j 0.3 pi, and that's minus a pi delta omega minus 0.3, plus 0.3 pi, and that's all over. I guess I could have I'll keep it written as the same way. We have j times 2 plus j 0.3 pi with a 1 on top. And if you look at table 4.2, we have a pair. So time domain signal is e to j omega naught t, and frequency domain we have a 2 pi delta omega minus omega naught. Now using this right here, well, if we put a 2 right there, if we multiply by 2 right there, and then we can squeeze a 2 in here. It's possible. 2 j omega, and we'll do the same thing here. 2 j. I multiplied by 2 and divided by 2, so I did not. It's the same as multiplying by 1. I multiplied by 2 over 2, which is the same as multiplying by 1, so we didn't change anything. So now these part right here and right here look exactly like something from our table. And like I said, this and this, they're complex numbers, but they're numbers. So we just treat them as coefficients. So that means that h of t is going to be equal to, we will have e to the j 0.3 pi t, and that's over 2j 2 plus j 0.3 pi. And I see real quick, this one should have been a minus sign right here. Made a boo-boo. That should have been a minus sign. This came from right there. and then we have a minus, and we have an E. Now, the same little flip right here. If you see, we have a negative omega naught, right? This is what it is. So omega naught has that negative sign in front of it. So we need to treat this as a minus negative 0.3. So we get e to the minus j 0.3 pi t, and that's all over 2j 2 plus j, or 2 minus, excuse me, minus um, 0.3 pi. And that's it. That's the final answer, or that's a acceptable final answer. You could make some. We can make a sinusoid out of this because we have an e to a j minus an e to the negative j with the same coefficients over 2j. But you don't have to do that unless it specifically states, and this question doesn't specifically state that. So here we are, and here is our time domain overall impulse response. Thanks.